So these are some chemical reaction indicators. These are some ways that we know a chemical reaction has taken place, okay? Color change is a big indicator for us. So if we mix together two clear things and we get out something that's yellow or pink or blue or whatever, that's an indicator for us that some sort of chemical reaction has taken place. Endothermic, exothermic, do we know the difference between those two things? Right, so one of them absorbs heat, right? One of them absorbs heat and makes the surroundings colder. One of them gives off heat and makes the surroundings warmer. Okay, so they can do different things. We talked last year, I remember, about endothermic, exothermic chemical reactions with examples of like hot hands or the ice packs you pop, right? Those are all examples of that. Glow sticks have a color change. That's a good indicator for us that a reaction's taken place, or they emit light. If we have formation of a gas, how would we know that we have formation of a gas? Okay, maybe it puts off a smell. What else? How would we know if we've got liquids being mixed together? How would we know that a gas is forming? Okay, amounts of liquid could change, but bubbles is the one I was thinking of, right? If you've got things that start bubbling, that's not due to a heat increase, that's not due to boiling, that's a good indication that a reaction is taking place as well. Okay, think about like the baking soda vinegar thing, right? You've got bubbles that form when that happens, so that's some sort of neutralization reaction. And then formation of a precipitate. Do you remember what precipitate means? Precipitate is a solid that forms out of two liquids. Okay, if we mix together two liquids and we're left with some sort of solid thing left over, we're going to have what's called a precipitate. All right, with our chemical equation is just the written word of a chemical reaction, the written form of a chemical reaction. We have to have correct formulas for products and reactants. Remember, if we write down, sulfate instead of sulfites or whatever, nitrate instead of nitride, our equation is not going to balance. We've got to make sure that we've got our balance or our formulas written correctly so that we can satisfy the law of conservation of mass. These are common symbols that we use in chemical equations. What's the S? Solid, liquid, gas. Aqueous. Do you remember what aqueous means? It's dissolved in water. So we're still only talking about like the actual compound. We're not talking about the water it's dissolved in. The water kind of just gives a place for the reaction to happen. So if we would see something like this, NaCl, aqueous, that would just mean that salt is being dissolved in the water, and the water has no I don't know. It's not changing the reaction at all. Water's not part of the reaction. It's just the place where the reaction is taking place. Okay. If we use coefficients, where do they go? In the front of a compound. Okay. And that relates to the whole compound. It tells us the relative number of molecules if we're talking about an atomic level. And it also tells us the relative number of moles when we start dealing on a bigger level. So it allows us to figure out how many of those molecules need to go together to satisfy the law of conservation of mass. Okay. We've got the list of 7 diatomics. Do you remember what those 7 diatomics are? Our periodic table is covered up.
Is it iodine?
Do you have your periodic table out? Why don't you go ahead and grab your periodic table? So our 7 are hydrogen plus nitrogen, oxygen, all that kind of stuff. And that means they have to exist with a partner of their own kind, okay? Sorry, is that skipping or no? Good. Okay, simple balancing. Let's review this first one real quick. I like to make the list. I think you guys might be advanced enough right now. You don't need to make a list to get your balancing done, but you're welcome to do so. Without the list, I'm going to look automatically at aluminum. I know that needs to change to a 2. I've got 6 bromine. That needs to change to a 3. That's really simple balancing, right? Because nothing on the left side was affected by me adding a coefficient. The second one down here is a little bit more of a challenge, so I want you to try that one on your own. I'll give you a few minute head start to kind of get that one going, and then I'll get it up here on the board as well. right, now you're going to build and balance based on our written form. So now we've got it. You need your periodic table of ions. If you don't have that out, you'll need your periodic table of ions. This says aqueous nitric acid reacts with solid magnesium hydroxide to form magnesium nitrate and water. So in this case, they actually did give you the products. Okay? So you've got to go nitric acid, magnesium hydroxide, to magnesium nitrate and water. Now, having it aqueous or solid, whatever, that doesn't affect how we write or build our reaction. So that part's not going to change for right now. Eventually, we will learn kind of why those things are in there, and we will figure out how to predict their states of matter. But for right now, it doesn't change the way we build and balance. Okay. My first step, if I don't want to make my list, I immediately see there's a nitrate on both sides, so I kept that together. But immediately I saw we've got 2 nitrates, but only 1 on the other side, so that's where I started. From there, I've realized, okay, I've got 2 hydrogens here and 2 more there, so that gives me 4. That's where I had to come and bring that there. So you notice that oxygen is kind of in a couple different places because it doesn't keep hydroxide on both sides. So you did have to kind of double check that one. But otherwise, without the list, you should feel yourself kind of bouncing back and forth from one side to the next. Is that how you kind of work? Is that the rhythm you guys mostly work in? Okay, very good. So pick your easiest change and then just go from there. All right, we're going to get into converting with mole ratio and converting mole to mole conversions. That's kind of where we're going to go today. The mole ratios tell us the conversion factor between one compound and another, right? Do you remember the mole ratio step in our conversions? That's the only place that you can change compounds because it's the only kind of true relationship we have from one substance to another. If we try to compare grams of hydrogen to grams of oxygen, those give us 2 completely different quantities, right? 1 gram of hydrogen would be a whole mole of hydrogen atoms, but 1 gram of oxygen would be 1/16 of a mole of oxygen atoms. So we can't compare them in grams. We have to compare them in moles. And so that's why moles is our middleman, right? That's our conversion factor. All right. So if I was going to look at this one right here, if I asked you the mole ratio between potassium chlorate and oxygen, what would you tell me? Potassium chlorate and oxygen gas, what would you tell me? What's my mole ratio? 2 to 3, right? 2 to 3. When it goes into our T-chart, it just goes in exactly as we follow our units, kind of let our units lead there, but that's exactly our mole ratio, okay? All right, let's try one here. How many moles of lithium hydroxide are required to react with 5 moles of carbon dioxide? Okay, so we start with what we know. You guys might even be to a place where you're able to predict, not even without the chart, right? You might be there. That's completely fine. 5 moles of CO2 moles of CO2 to moles of LiOH. And that's it, right? Because I want moles, and I'm starting with moles. So here's my mole ratio step right there. So I'm just going to put in 1 to 2. So that means I'm going to need 10 moles of LiOH. When you have nice round numbers like this, it's going to be easy for you to just be able to predict that. I think you could have looked at that right there and said, I need twice as much lithium hydroxide as I do carbon dioxide. And if you can do that, that's great. That's going to save you time. So you don't have to have the chart every single time, especially when we have nice, pretty round numbers like that. Okay? Do you feel okay about mole to mole conversions? We're good with that? Okay. How many moles of O2 will result from the decomposition of 0.66 moles of hydrogen peroxide? How do I know which one's hydrogen peroxide? Yeah, you know it's not the other two, right? If you don't know what it is, you got to go process of elimination. I know it's not H2O, and I know it's not O2, so it's got to be the first one. Okay, let's see here, balancing wise. I don't know, I think that's probably it. So 0.66 moles of H2O2. Again, we might be able to predict that one a little bit different because our mole ratio, right? But the chart still does the math for you perfectly fine. So I'll let you kind of use that as much as you need. All right, now let's go mole to grams. Now we're going to use, what's our conversion factor when we need to go moles to grams or grams to moles?
Or not, you say grams.
Grams to moles is molar mass. Yep, grams to moles is a molar mass, okay? So, let's see here. Here's our chemical reaction. It says, what mass of grams in glucose is produced when 6.4 moles of water reacts with carbon dioxide? This one's a little more difficult to just predict, right? You're probably going to have to do the math on this one, but we got to start with balancing. That's what I had when I balanced it. Let me know if you guys have something different than that, but that's what I got. Know what we had? Okay. Now we're just going to go ahead and solve, right? We start with what we know. 6.4 moles of H2O. I'm going to go moles of H2O to moles of glucose. And then I'll keep going moles of C6H12O6 to grams. So my mole ratios go in here, 6 to 1. In the mole ratio step, we get our numbers directly from our balanced equation, remember? So now in grams right here is going to be our molar mass. I ended up with a molar mass of around 180. Okay. And so when I plugged that in, I ended up getting 192 grams of glucose. Does that answer seem like it's rational? right? We started with 6 moles of it. Our ratio ended up being about 6-to-1, which means we were going to produce roughly 1 mole of our substance, or a little over 1 mole of our substance, which is exactly what it came out to be, right? If 1 mole weighs 180, we got it to be 192. Okay, do we feel like this is easy?